आज हम लोग बात करेंगे मिक्सिंग रूल के बारे में। अभी हम लोग जो टॉपिक चल रहा है वो है पार्शियल प्रॉपर्टीज ऑफ सॉल्यूशन और पार्शियल मोलर प्रॉपर्टीज और मल्टी कंपोनेंट मिक्सचर। जब हम बात करते हैं मल्टी कंपोनेंट मिक्सचर का, और जब हम मल्टी कंपोनेंट मीन्स मोर देन वन कंपोनेंट, तो जब हम दो कंपोनेंट को आपस में मिक्स करते हैं तो उसका भी एक रूल होता है। मीन्स मिक्सिंग एज ए केमिकली हम सिंपल दो कंपोनेंट को लेंगे और पोर करके मिक्स कर सकते हैं, या फिर हम दो गैसेस को लिए और एक चैम्बर में सप्लाई करके हम उसको मिक्स कर सकते हैं। बट जब हम उसके कांस्टेंट को कैलकुलेट करते हैं, कांस्टेंट इन द सेंस ये है कि जैसे हम वॉन्डरवाल इक्वेशन की बात करें, तो वॉन्डरवाल इक्वेशन में हमारे पास दो कांस्टेंट है ए एंड बी। हम आर के एस आर के इक्वेशन की बात करें, वहाँ पर भी हमारे पास कांस्टेंट है। यदि हम पेंग-रॉबिन्सन इक्वेशन की बात करें, वहाँ पर भी हमारे पास कांस्टेंट है। तो जब हम मिक्स करेंगे तो ये इन कांस्टेंट वैल्यूज को हम कैसे ऐड करेंगे, इन कांस्टेंट वैल्यू का हम मीन कैसे निकालेंगे, this is comes under the mixing rule. So according to mixing rule, the equation which express the mixture constant, the equation which express the mixture constant in terms of the pure gas constant are called mixing rule. Repeat once again, the equation which express the mixture constant in terms of the pure gas constant are called the mixing rule. तो हमारे पास जो कांस्टेंट है, हम जब उसको प्योर गैस कांस्टेंट के टर्म्स में, हम जो कांस्टेंट ऑफ द मिक्सचर है उसको हम प्योर गैस कांस्टेंट के टर्म्स में मेजर करते हैं और उसको रिप्रेजेंट करते हैं, उसे हम कहेंगे मिक्सिंग रूल। Essentially the mixing rule are empirical and their validity rests upon the agreement between the properties predicted by using them and experimental measured properties. So this is in between the experimental properties and the predicted properties. So the constant of the mixture is calculated by summation of yi yj into aij, yi yj aij, where am is a mixture constant, yi yj are the mole fraction of component I and j, and aii, which is actually the ai for the pure component constant, and ajj ajj is equal to aj, this is also the pure component constant. This is the aij. So aij, because when we are mixing two components, there are the interaction between these two components. So that's why this is the interaction constant and aij is written here. And when we have this all, there is another rule, that is the combining rule. अब हम उसको जोड़ेंगे कैसे? So this is comes under the combining rule. So the combining rule is the equation which provide the interaction constant in terms of the pure component constant are the combining rules. And this is in a two ways. Either we can add in the arithmetic mean or we can go for the geometric mean. So this is the arithmetic mean where aij is aii plus aji by 2, or aii is ai and ajj is aj by 2. Or by the geometric mean, aij is under root of aii ajj or equal to under root of ai and aj. So by using equation 1 and equation 2, we can get the mean of that, and here the mean of the constant is sigma of yi ai, or by adding the equation 1 and 3, we will get the mixture constant is sigma of I to c yi root over ai square. So with these methods, we can determine the constant of the mixtures. The mixing rule is commonly used for the cubic equations. Cubic equation जैसे हमने पिछले क्लास में देखा था, वैन डेर वाल इक्वेशन, आर के इक्वेशन, एस आर के इक्वेशन, पेंग-रॉबिन्सन इक्वेशन. So these all equations are the cubic equations, and these equations we have the application of this. Like I just started in van der Waal equation, we know that P is equal to RT by V minus B minus A upon V square. So in this van der Waal equation, there are two constants A and B, and this is for the pure component. If we have multi-component, then there will be the constant AI and AJ. So when we use mixture of this and determine the relation for P, So now the AI and AJ will AM will become, and that AM we can calculate in this manner. So that's why this mixing rule and combining rule is applicable for the cubic equation of state. There are the final term we can write AM is equal to sigma of I to j when interaction is taking place. This is what about there when there is no interaction. But if there is an interaction between the components I and j, so we can write AM is equal to yi sigma of yi yj under root ai aj 1 minus kij, where ki is the new term and this is known as the binary interaction parameters. This is known as binary interaction parameters. Similarly, here B is there, so B mean of this constant is sigma of yi bi. The binary interaction parameters is basically obtained uh, better agreement between the experimental values and the predicted values. Okay. There is one more thing is that the binary interaction parameters is determined while putting the experimental value over the equation of state, and this value is likely to 0 most of the cases when there is no data were available. So by using these techniques, mixing rule and combining rule, the scientists like Betty Brisbane and Benedict Waugh and Knapp, these all three were given their own mixing methods to determine the constant AI, AM and BM. So with the use of this, when we put the value over these parameters, suppose that we know the value of mole fraction of yi, yj, means we have two parameters. Suppose we have binary system, and in binary system we know the mole fraction of one component, another component we can determine, and we have the value of ai and aj. So in that case we can determine the value of am if there are no further information is given. If the value of kij is also there, then it is very easy for us, otherwise we consider it 0. So this way we can use such method to determine the constants. We have some more application of the mixing rule or multi-component system, so let us see those also. So अब हम लोग एक एग्जांपल लेंगे एंड उस एग्जांपल में हम देखेंगे कि कैसे हम कांस्टेंट जो है मिक्सर का हम डिटरमाइन करते हैं, कांस्टेंट ए एंड कांस्टेंट बी. So केमिकल इंजीनियरिंग थर्मोडायनेमिक्स रिटन बाय YVC Rao 2009 एडिशन, उससे मैंने एक एग्जांपल को लिया है. क्वेश्चन है द वैंडरवाल कांस्टेंट फॉर n-butane and n-octane are for n-butane A is equal to 1.3874 Pascal in bracket meter cube per mole whole square and B is equal to 0.1163 into 10 power minus 3 meter cube per mole. Similarly for n-octane A is equal to 3.7890 Pascal in bracket meter cube per mole square and B is equal to 0.237 into 10 power minus 3 meter cube per mole. We have to estimate the van der Waals constant for an equimolar mixture of n-butane and n-octane. So we have to determine the value of van der Waals constant A and constant B for the mixture. Okay. And one more information is given, that is for an equimolar mixture. Equimolar means if there is two components butane and octane and both are in equal proportion. So here the value of y1 is equal to 0.5 and y2 also 0.5. The value of a1 is this one and b1 is this. Similarly this is a2 and this is b2. हम फार्मूला जानते हैं कि am is equal to sigma of y1 ij yi yj bracket under root ai aj in bracket 1 minus kij. So in this question there is no terms talking about the interaction parameters. So that case we consider kij is equal to 0. So our equation is now reformed and this will be become, when this becomes 0, so am is equal to sigma of ij yi yj under root ai aj. Now when we open this expression, so it will become like that I is 1 and 2, j is 2. So yi yj. So at the case when y1 and means when I is 1 and j is also y1 a1 1, then second case y1 y2 under root a1 a2, and then y2 y1 under root a2 a1 plus y2 y2 under root a2 a2. So by adding of this one, y1 into y1 is y1 square, and under root a1 into a1 is a square, it will comes out so a1. Then similarly y1 y2 root a1 a2 and y2 y1 root a2 a1. So summation of this will give you 2 y1 y2, and the same way y2 into y2 is y2 square into under root a2 a2 is a2 square, and then it is a. Now from here, from the problem, y1 is 0.5, y2 is 0.5. So I kept the value, and corresponding the value of a1 and a2 be put here, and while solving this expression, the value of the constant A for the mixture is 2.4405 Pascal in bracket meter cube per mole whole square. Similarly, when we open this one, so this is y1 b1 plus y2 b2. So y1 is 0.5, b1 is 0.11, 63 into 10 power minus 3. So I kept outside the bracket, plus 0.5 into 0.237 into this. So while solving this expression, the value for b is 0.1769 10 power minus 3 meter cube per mole. So with the known value of constant of the pure component or individual component in the mixture, and with the known value of mole fraction of the component in the mixture, we can calculate the constant, van der Waals constant A and B with the use of this formula. So these are this very easy. Similarly, like we have seen the Benedict BVR equation or Knapp equation and Beatty-Bridgman equation. So there are some formulas were given to calculate the A, B and other constant, and when we put those known values over the formula, we will get the value of this mixture of the constant. So this is the very easy way to find the constant value for the मिक्सर. अभी हमने देखा कि कैसे हमने कांस्टेंट वैल्यू ऑफ मिक्सर का डिटरमाइन किया. सिमिलरली हमारे पास एक और कांस्टेंट आता है जो है कंप्रेसिबिलिटी फैक्टर जेड. जब हम बात करते हैं मिक्सर की, तो ऑब्वियसली जो कंप्रेसिबिलिटी फैक्टर ऑफ मिक्सर विल बी आल्सो द चेंज. तो इसको कैलकुलेट करने के दो मेथड्स हैं, एक है बाय एमागेट्स लॉ एंड दूसरा है बाय डाल्टन्स लॉ. So Avogadro's law is based on the volume, additive volumes, and Dalton's law is based on the additive pressure. तो देखते हैं Avogadro's law क्या है. Avogadro's law is additive volume state that the total volume of a mixture of ideal gases is equal to sum of the volume of the pure component at the same temperature and pressure of the mixture. So the Vm additive volumes is the summation of mole fraction into volume of the that component, pure component, when the condition is ideal gas, right? So Vm is equal to sigma of Ni Vi. Let's do some operation, multiply, because the in the mixture the pressure is constant and temperature is constant, so P upon nRT in both the sides. So P into Vm upon nRT and P by nRT into this. Now further solving this one, so we know that for the real gas pure component PV is equal to ZRT, or Z is equal to PV by RT. So for this case Vm is there, so Zm. So Zm is, this term is now replaced with the Zm, and Zm is equal to P upon nRT into sigma of Ni, and this Vi is for the pure component, I can write Zi RT by P from the here. So this term is, expression is now further simplified. यदि हम यहाँ पर देखें तो RT बाहर ले सकते हैं, तो RT कैंसिल हो जाएगा, P कैंसिल हो जाएगा, तो बचा क्या N. N will be, हम इनसाइड ले लें, So Zm is equal to sigma of Ni upon N, this N will be inside, N into Zi. So N upon Ni, this is the mole fraction. So mole fraction Yi represented by Ya. So Zm is equal to sigma of I Yi Zi. So for the mixture, when we use the Avogadro's law, where additive volume is pictured for the ideal gas mixture, the Zm is represented by sigma of I Yi Zi. Another method is given by the Dalton's law. So Dalton's law is based on the additive pressures. So here mixture temperature is constant, and the n number of component is occupying the total volume V. So Zm is equal to Pm into V upon nRT, or Pm is nothing but the Pm is the additive pressure. So Pm is the sigma of Pi, where Pi is pure component pressure. Where Pi is pure component pressure. So I am written here P, capital Pi is equal to minus Pi. So where P is equal to, means capital P is equal to small pi only for the ideal gas. For real gas, this relation does not exist. So once again, Zm is equal to Pm into V upon nRT. Let's do some operation because Pm is the sigma of Pi. So V upon nRT into sigma of Pi. Now let's do some operation like that Ni upon Ni is multiplied in numerator and denominator, and then Pi into V upon RT. So this capital N is now rearranged to get some solution. So Ni upon Ni we can write Yi, and Pi V upon Ni RT, this is represented by the another term, that is the Zi dash. So what is Zi dash? Zi dash is PIV upon NIRT. This is also the compressibility factor, but the noticeable point is this Zi dash is not is equal to this Zi. Zi dash is not is equal to Zi, because of just because of here our condition was, in this additive volume we keep the temperature and pressure of the mixture, but here we consider the temperature of the mixture, but the pressure was the pure component. That's why these two are not equal. So by using the Avogadro's law and Dalton's law, we can determine the value of compressibility factor of the mixture, but with the both way we will get the different value. So this we will use as per the requirement of the our calculation, or as per the requirement of the problem. Now we will see fugacity of component in a mixture. So in a mixture, the fugacity is also different for the different components, and we are defining that A phi k, and that is also known as the partial molar fugacity. So for pure substance, we are defining the fugacity is dg is equal to vdp is equal to RT d ln f at constant temperature. Or if you want, you can keep cap here, and G minus Gi naught is equal to RT ln f by P is equal to P0 to P V minus RT by P dP, and f by P, when f by P tends to 1, where P tends to 0, मीन्स लो प्रेशर की तरफ जाएगा तो फ्यूगिसिटी जो है वो प्रेशर की, फ्यूगिसिटी एंड प्रेशर का जो रेशियो 1 के हो जाएगा, मीन्स फ्यूगिसिटी जो है वो प्रेशर के इक्वल हो जाएगा. Similarly, for the mixture, partial fugacity of component I is defined like that dgi bar is equal to Vi bar dP is equal to RT d ln Fi, and referring the equation 2, for the component I we can write the equation in this way, where A phi cap upon Ya P tends to 1 as P tends to 0. So in a mixture, when we take the departure of this Gibbs energy, so RT ln A phi naught upon A phi upon A phi naught. So A phi naught is representing actually the pure component fugacity when the component at the ideal gas, means at the pressure when component behave like an ideal gas. So when the component behave like an ideal gas, this goes to the pressure P, and because this is the partial, so this is the multiplication of the mole fraction of the component into the total pressure. So A phi naught we can write YIP, and then the rest of the part P0 to P Vi bar minus RT by P dP. So here it is clearly mentioned. So why this is coming? Because this is A phi naught is nothing but the YIP. Just I have explained how this is coming. I am repeating once again, because A phi naught is the naught indicating that the pressure is very low or the component is behaving like an ideal gas. So when the component is behaving like an ideal gas, so in a mixture of the ideal gas, the partial pressure is equal to the fugacity of the pure component, and that moment the partial pressure is equal to the YIP. That's why it is written here. And Fi YIP is equal tends to 1 as P tends to 0. Now let's rearrange this equation. VIdP is equal to RTdl and Fi. So I have taken this one left hand side and VIdP in right hand side. Now dividing dP here, so RT dln Fi by P, dou P is at constant temperature and component, it is equal to Vi. So when I will divide dP here, the Vi will be come here. So Vi we can write dgi bar upon dP. How? We can see. We know that dg is equal to minus sdt plus vdp. So let's divide dP both sides, keeping temperature and component constant. So when temperature is constant, this term goes to 0, and when dou P by dou P is there, so this term goes to 1. So for partial molar volume, this will be written like this. So Vi bar is nothing but the dou G I bar uh, upon dou P. So it is here. And we know that the Gi bar without the partial molar Gibbs free energy is nothing but the chemical potential. So I am written here the chemical potential. Now this in this what I did is I multiplied by dou V by dou pi, dou V by dou V in numerator and denominator when keeping the same temperature and component constant. So by rearranging this will become dou mu I by dou V in bracket when temperature and component constant into dou V by dou P temperature and component constant. Putting this to over here, so R T dou ln Fi by dou P T and J is equal to this term dou mu I by dou V T and J into dou V by dou P when temperature and component constant. Now I will rearrange this one. So when I will rearrange this one means this term I will shift to the left hand side. So dou P by dou V T and J is equal to d mu I by d. This is the one expression, or we can further we simplify here, because dou P and dou P is there, so these two will be cancelled and the final term is RT dou ln Fi upon dou V T and I is equal to dou mu I by dou V. This is the expression for fugacity of component I. Similarly, we have to find out the same expression in terms of the pressure, and when we difference this or these two, we will get the ratio of A phi cap upon P. So this is our target. So for reaching this target, and this is nothing but the phi, we know that. So A phi cap upon P is equal to phi, and this is our target. So for that, we have used another known relation, that is the Helmholtz free energy relation. So Helmholtz free energy A is a function of temperature, volume and number of components. We know that from the Maxwell relation itself, by the applying or by the determine the Maxwell relation, we use same expression. So dou square A by dou V dou Ni is equal to dou square A by dou Ni dou V. So in denominator, the differential terms have exchanged their place, but mathematically this will not harm. So let's open this one, so dou by dou v into dou a by dou ni Tv and J. In this case, Tv temperature, volume and Nj is constant, and here temperature and component is constant. Similarly, when you open this, so dou by dou ni, dou a by dou v, temperature and component is constant here, and outer side in this case the temperature, volume and component is constant. Okay, where J is not equal to I. So we know that, let's keep this expression 6. We know that dou A is equal to minus HDT minus PdV. So let's, what we need is our need is dou A by dou Ni, and so dou A by dou Ni we know that from the previous also, dou A by dou Ni is mu I, so dou by mu I. Now dou A by dou V, so let's divide dou V both side and keeping temperature and number of components constant. So temperature and number of component constant. So when temperature and number were constant, this term goes to 0 and dou V by dou V is goes to 1. So the term is dou A by dou V T and J Ni is equal to minus P. So this minus P I kept here. So now dou V by dou V, dou mu by dou V in bracket T and J is equal to minus dou P by dou Ni T V and J, where J is not equal to I. This is another term 6. Now by substituting the value of equation 6 into the equation 5, the relation become RT dou ln Fi by dou V T and J T and I is equal to, here dou mu I by dou V T and I, and here dou mu I by dou V T and I is minus dou P by dou Ni T V and J. So same is replaced here, dou P by dou Ni T V and J. So this is our another expression. Now we have reached the term in the terms of A5. Now we have to further find the relation for ln P. So we know that we will apply one operation here. We know that ln PV is equal to ln P plus ln B. As we know, A plus ln A into B is equal to ln A plus ln B. So ln PV is equal to ln P plus ln B. Now differentiate both side and with respect to V and multiply RT. So differentiate with respect to V both side and multiply RT as well. So when I will differentiate here, so dou ln PV by dou V, where temperature and number of component constant is equal to dou ln P, so dou ln P by dou V, temperature and energy constant, plus dou ln V, so dou ln V by dou V T and J, and then thereafter multiplied RT in both sides. So here, while applying this, now I will rearrange this once again. So RT dou ln P by dou V, there is same, but dou ln V by dou V. So ln V, when we differentiate this one, ln V, dou ln V, so it will become 1 by V. So the term is RT by V. Now after rearranging, because my target is here to find dou ln P by dou V T and J is equal to RT dou ln PV, because this will be means this will be go right hand side, this will become left hand side, and then multiplied the minus sign, or you can simply this part you shift here and then after rearrange, so you will get the same expression. So this term RT dou ln P by V dou V, this RT I shift right hand side, left hand side first, and thereafter whole I have exchanged, so there is no problem with the minus symbol. So RT dou ln V dou V is equal to RT dou ln PV by dou V into at the temperature and component constant minus RV. Let's give this expression 7. So by separating equation 8 from the equation 7, so we can write RT dou ln Fi by dou V T and J minus RT dou ln P dou V T n is equal to minus dou P by dou N TV Ni minus RT dou ln PV by dou V TNI plus, because minus is there, we are separating, so plus RT by V. Now this the rest of things were constant, similar in both cases. So ln Fi minus ln P, we can write ln Fi by P. So therefore RT dou ln Fi by P upon dou V is equal to RT by V minus rest these two terms. Dou P by dou Ni TV Nj minus RT dou ln PV by dou V. Now we have to further simplify this term. So for that, multiplying dV both side and integration with respect to V while applying the limit V infinity to V. So with this term, first multiply dV in both side and then put integral symbol and then we apply the limit V infinity to V. So by solving this, the RT ln Fi by this minus because this will become, so for V is this and for V infinity it will become RT ln Fi cap by P V infinity is equal to, these two terms will be constant and this term we will further integrate, so that this term will come minus RT ln PV minus RT, so dou by dou V integration of dV will come ln PV. So ln PV is there and limit is what? V infinity to V. So when limit is V infinity means it's again ideal gas condition, and at the ideal gas condition when V goes to infinity the PV goes to nRT and V is the V when PV is equal to PV. So the limit is nRT to PV. Now further solving this, RT ln FIP minus, here when the condition is goes to the ideal gas because V infinity is there, so the pure component fugacity is written like that Fi naught. So this Fi naught is defining it is a pure component fugacity, and then right hand side is this as it is minus RT ln now PV by RT, because ln A minus ln B, so ln A upon B, so ln PV upon nRT. Now further simplify this one, so RT ln A minus RT ln B, so ln A upon B, so FIP into, because this is upon, so numerator will go to the denominator and denominator will comes to the numerator, so P upon Fi naught, P will be cancelled here and Fi cap upon Fi naught will become. Similarly in right hand side V infinity to V, this part is because this is already in a volume explicit terms and we have the various equation of state which we can use over here in volume explicit terms. If it is comes to the pressure explicit terms, then it will be difficult for us, and that term we have to change for the volume, but it's already in volume so need not to work over here. And we also know that for the ideal gas, for the real gas, the PV upon nRT is equal to Z, and for the ideal gas PV is equal to RT. So PV upon nRT for real gas, PV is equal to ZRT. So PV upon nRT we can write here nRT is equal to Z. So that is placed here minus RT ln Z. Now by solving we got Fi caret upon Fi naught is equal to RT ln Fi upon Yip. So we know that the Fi naught this is the fugacity of component I in a mixture, right, at the pressure is very low, and that moment in a mixture this is written this is written YIP. So now we have put here Fi naught YIP, Fi naught is equal to YIP here, and rest part is as it is, and this part is replaced with the new term, that is the phi I caret, and this is known as the fugacity coefficient of the component I. So with the help of this expression, while using the various equation of state, like we have seen for enthalpy departure term or entropy departure term, we can also calculate the fugacity coefficient of component I. So with this, we are concluding our part of the multi-component mixture for the chapter of fugacity and fugacity component or fugacity coefficient, and further we will see the various rules which will help us to determine the properties of the solution. So till that, be connected with us and learn thermodynamics and improve your knowledge in the field of thermodynamics. Thank you.